Welcome to The Explainer. Today, we're diving into the fascinating evolution of the internet. We'll trace exactly how the web went from these basic, static digital blueprints into the incredibly dynamic, reactive applications we use every single day. If you've ever wondered how your browser actually talks to a server, or how a web page instantly knows you typed letters into a phone number box, well, you're in the right place. So, let's jump right in.
To ground our exploration, I want to share a proverb straight from the course material. I hear and I forget. I see and I remember. I do and I understand. You see, when it comes to web programming, having a hands-on builder's mindset is absolutely crucial. It's one thing to just read about how the internet works, right? But to truly grasp it, we literally have to look at the exact structures, the network protocols, and the scripts you'd use to build a page yourself.
Here's our roadmap for today. We'll follow the exact evolution of the web, starting with designing your digital hub, then moving on to the language of the web, anatomy of a web request, bringing pages to life, and finally, web memory and interactivity.
All right, Section 1, Designing Your Digital Hub. Let's start by laying the absolute foundation of our digital house using HTML and CSS. To build a successful central hub, you really need a solid HTML skeleton. Think of it like framing a house. A great page organizes its content logically using dedicated, categorized sections, like personal info or your skills. It also needs strong navigation. We're talking anchor links so users can seamlessly jump around within the same page, internal links to other pages on your site, and external links to outside sources. Combine all that with a prominent name, a personal photo, and at least one properly structured table, and boom, you've got the raw materials for a really robust digital hub.
Now, let's be honest, raw HTML isn't exactly pretty. So to handle the interior design of our digital house, we rely on styling, specifically by keeping our CSS separate from our HTML. You really want to keep your overall aesthetic rules in an external CSS file. Why? Well, it keeps your HTML super clean and lets you style multiple pages all at once. It's a huge time saver. Inline CSS, where you write the style directly into a specific HTML tag, should be used very sparingly. Reserve that only for tiny, highly specific adjustments, like a quick width tweak or making one little piece of text bold.
Moving on to Section 2, the language of the web. Now that we have the structural blueprint and styling of our digital home, we need a road network and delivery trucks to actually move it across the globe.
This brings us to the famous client-server model. Think of your web browser as the client asking for information, and somewhere else on the internet is a web server holding those pre-created HTML, CSS, and image files. To get those files, your browser sends out an HTTP request over the network. The server catches that request, processes it, and sends back an HTTP response containing your data. It's a simple, elegant loop, but the efficiency of that loop has changed drastically over time.
And that is exactly where the delivery system evolved. Under the older HTTP 1.0 protocol, every single request, say one HTML file and 3 images, required its own brand new connection. It was literally like shutting down an entire highway after every single delivery truck went through. You can imagine the massive server overhead that caused. HTTP 1.1 was a total game changer. It solved this by keeping a persistent connection open by default. So now, your browser can efficiently download all the images and scripts on a page at once, without having to constantly knock on the server's door.
Next up, Section 3, Anatomy of a Web Request. We've seen the high-level map, but let's zoom in on exactly how your browser asks for a file using what's called a GET request.
The course material walks us through a classic example using Yahoo. When you hit Enter, Step 1 is just you typing the URL. Step 2, your browser translates that URL into an IP address and opens a TCP connection, typically on port 80. Then comes Step 3, the actual request. The browser sends a byte stream saying GET, followed by the file path and the HTTP version. Finally, in Step 4, the server replies with its headers and the HTML payload itself before closing the connection. It all happens in the blink of an eye.
When the server replies in that final step, it always includes a status code to tell your browser exactly what went down. You're probably familiar with some of these. A 200 means OK, everything processed perfectly. A 301 means the document moved permanently. And of course, there's the infamous 404 not found, which just means the file you wanted isn't on the server. Oh, and if the server itself crashes or gets overloaded, you might see a 500 or 503 error. If we pull back the curtain entirely, a raw telnet connection reveals this hidden conversation. Look at the exact headers the server sends right before delivering the HTML code.
It's sharing metadata like the exact date, the server software being used, when the file was last modified, and the content length in bytes. All of this invisible metadata is processed by your browser in a fraction of a millisecond, way before the page even starts to render on your screen. Pretty cool, right?
Okay, on to Section 4, bringing pages to life. Our house is built and our delivery network is optimized, but right now, it's just a static display. To make it a smart home with electricity and plumbing, we have to transition from static text to interactive scripts. This is where client-side programming comes into play. As we know, HTML is fantastic for static layouts, but client-side scripting languages, mainly JavaScript, are embedded right into the HTML and run locally on your own machine. Because they're interpreted by your browser instead of being heavy, compiled software, they add incredibly fast logic and responsiveness without eating up massive amounts of bandwidth.
Now, this introduces a totally different style of programming. Unlike traditional programs that just run sequentially from start to finish, JavaScript relies heavily on an event-driven model. Basically, the code just sits quietly in your browser, waiting. It's waiting for an event, maybe a mouse click, a button press, or the page finishing its load. When that event happens, it reacts. So the programmer isn't controlling the sequence, you, the user, are.
This user-driven interactivity is primarily anchored in HTML forms. Forms group together elements like text boxes, radio buttons, and checkboxes. And here's the key. Each of these elements acts as a trigger. For example, clicking a button can fire an on-click event. Or if you type in a text box and then click away, that can trigger an on-change event, which immediately runs a piece of JavaScript to analyze what you just did.
One of the absolute most common applications for this is form validation. Let's say you're building a temperature converter, and you ask the user for a number. But what if they type the word apple? Well, your math functions would completely break. To fix this, you create an input field, add that on-change trigger, and call a custom validation script. The script checks if the value is literally not a number. If it's illegal, the script instantly alerts the user and resets the box. And the best part? It does all of this before the server is ever even contacted. And that brings us to our final section, web memory and interactivity. Let's explore automated timing and memory.
Let's talk timing first. The set timeout function is a remarkably simple but powerful tool that lets developers introduce automated delays. You just hand it a piece of JavaScript code and tell it how many milliseconds to wait before running it. This is exactly what powers features like automatically redirecting you to a new page or updating a countdown clock that's ticking away the days, hours, and seconds until graduation.
But what about memory? How does a website actually know you've been there before? Well, the answer is cookies. Cookies are these small data strings saved directly onto your computer by the browser. They're stored simply as attribute value pairs. Using JavaScript, a web page can read and write these cookies locally to remember things like your name, your past purchases, or how many times you've visited the site. It's what makes your experience feel seamless across different browsing sessions.
When you combine all these tools, you really start to see the immense power of client-side scripting. JavaScript can reach right into the document object model to read and write specific HTML elements. It handles complex date calculations, generates random numbers for a dice game, manipulates massive arrays of data, and manages your long-term user memory through cookies. It literally takes a static layout and transforms it into a highly reactive living system. As we wrap up this explainer, I want you to think about how all these pieces, the structural HTML blueprints, those complex network protocols, and the event-driven interactive scripts, seamlessly blend together to create the modern web. I'll leave you with a provocative thought. Consider the very screen you're looking at right now. What hidden programs are patiently waiting for your next click today? And what cookies are silently remembering what you do? Thanks so much for joining me, and keep exploring the architecture of your digital world.